All right, so we're in section 4.3.
First period, second period. The other advantage to me is 7 dogs in 1 day, like the entire period.
All right, so I've had a few students, as we're talking about the unit circle, they say, so we're talking about sines and cosines and all this stuff. What does this have to do with Sohcahtoa? And we're going to, we're going to make that connection. So let me draw a right triangle here. And we'll call this angle theta. And this is our right angle. And we're going to, this should all be fairly familiar. We're going to label our triangle. This side is the hypotenuse. We're talking about this angle theta, so this, we call this the adjacent side, and this side the opposite side. And we're going to talk about our sine, cosine, and tangent based on this triangle. So, thinking back to Sohcahtoa, sine of theta. How do we find the sine of theta? Opposite over hypotenuse. I'm going to use abbreviation here. Opposite over hypotenuse. Cosine theta. How do we find cosine? Adjacent over hypotenuse. And the tangent of theta. Opposite over adjacent. And then we'll talk about our reciprocal functions. Cosecant, all we do is flip over the fraction. Cosecant of theta is hypotenuse over opposite. Secant, we're just flipping these fractions. Hypotenuse over adjacent. And cotangent is adjacent over the opposite. So these are all of our trig functions based on this right triangle. Let's draw a unit circle here and see how these are. Let's talk about how these are connected. So here's my circle. There's my center at 0, 0. Draw my x and y axis here. And here's my point on the unit circle x, y. And we said on the unit circle that the sine of our angle was y and the cosine was x. So we want to make a connection here. So how are these two related? What do we do to come up, well, one, what's special, what's important about the unit circle? Radius is 1, so let me draw the radius in here. We know that is 1 unit. Well, where did the x and the y come from? How can I think of the x and the y? How can I relate it to what we have up here? Just draw in a right triangle here. And we did that when we talked about putting our special right triangles on there. That's a right angle. This side of the triangle is y. That's how far up I'm going. And this side is x. And we said that if this is our angle theta, we said sine theta, and we could relate theta to a point on the number line that got wrapped onto the unit circle. Sine theta was y. Well, that's the opposite over the hypotenuse. The hypotenuse is just 1. And we said the cosine of theta was x. Well, that's the adjacent over the hypotenuse. So that's how these two are related. Our hypotenuse is 1, so we don't have to worry about it. We just get the x and the y coordinate for our sine and our cosine of our angle. That was part of the benefit of looking at it in terms of unit circle. And then we could do the same thing with our tangent and our cofunctions and our reciprocal functions. So it's all related to the circle. We can draw a triangle on the circle, and we get the same relationships that we had before. Now, a couple of things when we're talking about right triangles, and we're using these ideas, we're saying that theta is acute. So theta's less than 90. This is our 90-degree angle, so we can't have another 90-degree angle on that. So theta is acute, and when theta is acute, all of our trig functions are going to be positive. So when we're talking about right triangles, we're talking about acute triangles. So what I want to do is kind of re-emphasize some of the relationships that we have between the sides of our special right triangles related back to the unit circle, and then we're going to use these ideas to solve some problems. All right, so questions on our connections here. All right, so let me draw up a couple of special right triangles here. So this is going to be our 45, 45, 90. And we'll make our hypotenuse 1 to make our lives easy. And I'm going to make the hypotenuse 1, and this is my 30, 60, 90. And we're going to come up with the sides of these triangles and sides of the triangles and find our sines, cosines, and tangents. So for a 45, 45, 90, if the hypotenuse is 1, what are the lengths of the two legs? Square root of 2 over 2. How could we figure that out? We had that picture on our diagram for the unit circle. We have this triangle written on there. How do we figure that out? Or thinking about just geometry, if we had this shape and we wanted to figure out the lengths of those sides, what would we do? Any ideas? Well, first off, a 45, 45, 90 degree triangle is half of what kind of nice shape? Half of a square. So we know that a 45, 45, 90 is half of a square. So that tells us that these two sides have to be the same. And if we know the length of this diagonal, what could we use then to figure out the length of those two sides? What always works on this kind of triangle? Pythagorean Theorem. We could say a squared plus a squared equals 1. So 2a squared equals 1. And then we end up with each side being the square root of 2 over 2. So this comes from the 45, 45, 90 being half of a square. And we can use the Pythagorean Theorem to find our sides. All right, so let's figure out the sine of 45 degrees. We already know what it is. Sine of 45 is what? We can think of our unit circle, or we can look at this triangle and figure out the sine of our angle. It's going to be square root of 2 over 2. Cosine of 45 degrees. What's a cosine of 45 degrees? Square root of 2 over 2. Tangent of 45 degrees. 1. We should work on memorizing these. We're going to do the same thing with our 30, 60, 90 triangle. If the hypotenuse is 1, what is the length of this side? 1/2. And we can figure that out because a 30, 60, 90 is half of what kind of shape? Rectangle? It is half a rectangle, but that would let us figure out that this side is 1/2 and that side is 1. It's half of an equilateral triangle. So there's my equilateral triangle. All the sides are the same, so this whole side would have to be 1. When I drop a perpendicular there, it cuts it in half, so that would have to be 1/2. And then we know that the long side here is how long? Square root of 3 over 2. And we can find that using the Pythagorean Theorem. All right, so let's write our sines and cosines of 30 and 60. Sine of 30 degrees. Square root of 3 over 2, everybody agree? One half. 30 degrees is here, the opposite, 1/2. The hypotenuse is 1. So sine of 30 would be 1/2. Cosine of 30 degrees. What's that going to be? Square root of 3 over 2. Tangent 30 degrees. One half over square root of 3 over 2, which can simplify to square root of 3 over 3. So let me write that out here. I have 1/2 divided by the square root of 3 over 2. When I divide by a fraction, what am I doing? Multiply by the reciprocal. So 1/2 times 2 over square root of 3. The 2's cancel, and I get 1 over square root of 3, which rationalizes to square root of 3 over 3. So there's my tangent. Sine of 60 degrees. What's the sine of 60 degrees? Square root of 3 over 2. Cosine 60 degrees. 1/2. Tangent 60 degrees. Square root of 3. These come up so often that you should memorize them. At least memorize these and be able to get to these. But these angles come up extremely often. And then there are special angles from our unit circle. In radians, 45 degrees, please. How many radians? Pi over 4. 30 degrees, pi over 6, and 60 degrees, pi over 3. So these are angles that we use to build our unit circle. So these are important angles. Does anybody see an interesting pattern here, an interesting fact? Relationship between the sine and the cosine of these angles. How about this? The sine of 30 is the same as the cosine of 60. And how are 30 degrees and 60 degrees related? Complementary. So that turns out to be true all the time, is that the sine of a complement, the sine of an angle is the cosine of its complement. Why would that be? Let's look back at this picture. So if we're looking at this angle, aren't these two angles going to be complementary? Don't they have to be complementary in order for all three angles to add up to 180 degrees? Yes? So what happens to this side? This is the opposite of theta. This is the opposite of this angle. So the opposite and the adjacent switch around. So when we have complementary angles, two different angles in one right triangle, the sine of one angle is the cosine of the complement. And it's true of all the different functions and their cofunctions. That if we have complementary angles, the sine of the angle is equal to cosine of the complement, etc. So I want to write out those rules a little more formal. So these angles, unit circle angles, these quantities, they come up so often that we should work on memorizing them. And they're also how we get to the other points on our unit circle. So what we saw on the last page, we can write as the sine of 90 degrees minus theta equals the cosine of theta. The sine of the complement is the cosine of the angle. And that's true of all of our trig functions. The tangent of 90 degrees minus theta is the cotangent of theta. And the secant of 90 degrees minus theta is, the cosecant of theta. And it goes the other way around also. So if we have complementary angles, the angle and its cofunction, the sine, the cosine, tangent, cotangent, secant, cosecant, the function of one angle is the cofunction of the complement, and that's true of all of our trig functions. This relationship comes up not as often as some of the others, but it's a good one to have in your little bag of tricks. This one should be secant, yes. So basically it works in both directions, is what we're saying. So what I want to do is just do a couple of examples of using Sohcahtoa, using right angle trigonometry to solve some problems, and I want to talk about how we're going to do a couple of things in our calculator. Usually with triangles, when we're dealing with right triangles, they're going to give you the angles in degrees. So you want to make sure your calculator is in degree mode when you're calculating these things. If you have your calculator in radian mode from using the unit circle, you want make sure you check and see if the problem is given to you in degrees. All right. So here's an example of the type of problem you might need to solve. So we know that the sun is 30 degrees up from the horizon. It's shining on the top of the tree. So our tree makes a 50-foot shadow. And we want to know how tall is the tree. So what I recommend on these kinds of problems is draw a picture. One, because it helps you do the problem, and two, because it's fun to draw these pictures. So here's my sun and my tree. The sun is shining down on this tree and is casting a shadow. And we're saying that the tree is a nice vertical tree. It makes a 90-degree angle from the ground. And this angle, the sun is up 30 degrees, and the shadow is 50 feet long. And we want to know how tall the tree is. So what are we going to do here? So we want the length of the side of the tree, so let's call that x. We want the length of the tree. So what are we going to do to proceed with this problem? Grab our tape measure? Tangent? Why do we want to use tangent?
Because you have the opposite side and the adjacent side.
So we look at our triangle. We see this is my angle. We have the opposite, and we have the adjacent. So I'm going to write tangent of 30 degrees equals x over 50. A lot of people skip this step and go straight to writing x equals 50 tangent 30. That's fine as long as you get the relationship right. It's easy to flip this fraction the wrong way, just like it's when we're converting units. So it can be helpful to double check yourself this way. And then I'm going to say x equals 50 tangent of 30 degrees is, we just talked about it, square root of 3 over 3. Plug that in my calculator and I get approximately 28.87 feet. And you want to make sure your calculator is in degree mode when you find the tangent of 30 degrees. But you should know that the tangent, you shouldn't need your calculator to find tangent of 30. You should be able to figure out that it's square root of 3 over 3. So questions on that one? All right, another one. Let's say we have a flagpole. And it's held up by a rope. That is 35 feet long. And it's attached It's attached 25 feet from the base. And we want to know what angle the rope makes with the ground. So let's draw a picture. Here's my flagpole, my flag. It's held up by a rope. And my angle, that's a 90-degree angle. We're trying to find this. And we know this is 35 feet and this is 25 feet. So what are we going to do here? What relationship are we going to use? Cosine. We're going to use cosine because we have the adjacent side to my angle and the hypotenuse. So I'm going to write cosine theta equals 25 over 35. Now how do I find my angle? What is it? Inverse cosine. So I'm going to say theta equals inverse cosine of 25 over 35. And you can put it in your calculator just like this. Inverse cosine of 25 over 35. Make sure, so if your calculator's in degree mode, you'll get the angle in degrees. If your calculator's in radian mode, you'll get the angle in radians. And I'd recommend that you use the parentheses, because otherwise what your calculator does is inverse cosine of 25 divided by 35 if you don't use the parentheses. And so same thing if you have sine theta equals something, tangent theta equals something, you're going to use inverse cosine, inverse tangent, inverse sine, whatever it is, whatever trig function you have, you're going to use the inverse to find your angle. It depends on, so it would depend on how the question asked. So this one, it doesn't say, so you could do it either way. Usually, what I said was usually when we're dealing with right triangles, you're going to use degrees. And this comes out to be about 44.42 degrees would be this angle. All right, let's do one more example. We go back. Any questions before we move on from that one? Okay. So let's say we have this triangle. And this is my angle. And the problem says find the exact value of all 6 trig functions for theta. So what are we going to want to do here? So a couple of clues here. When it says exact value, that's a clue that you are going to write fractions, not decimals. So we want to write fractions here. If we were on the unit circle, we would be set, because we would know that the hypotenuse of my triangle was 1. But it doesn't tell us we're on the unit circle. It's not a point on the unit circle. It just gives us a triangle. So exact value means we want fractions. We're not plugging in these in our calculator and finding these things. So what do we need to do? We need to find the hypotenuse. So let's call the hypotenuse C. Does anybody know right off what C is going to be? Anybody recognize that? What is it? Anybody have it? One person in the last class recognized 17. 8, 15, 17 is a Pythagorean triple. So if you recognize that, you would know that C equals 17. If you didn't recognize that, what could you use? Pythagorean Theorem. Always works on a right triangle. So we could say C squared equals 8 squared plus 15 squared, and that tells us C equals the square root of 289, and we would end up with C equals 17. So now we know C equals 17. We can write all of our trig functions. So sine of theta, what's going to be the sine of that angle, Abby? Here's my angle. Sine of theta is, we're using Sohcahtoa. (15 17ths). Nice. So we're just writing fractions. That's my exact value. Cosine? Cosine of the angle, what's our cosine going to be? 8 17ths. tangent. What's going to be the tangent? 15/8. And then we're really done because the cosecant, what do we do to get the cosecant? Just flip the fraction. 17/15. The secant, we're just going to flip that fraction. 17/8. The cotangent, 8/15. And there's my exact value for my trig functions, all 6 trig functions for that angle. All right, questions? Okay. Homework, we're on page 280. There you go.